In this video, Control of Macro Segregation in Heavy Steel Ingots, I will present to you the principles we use to predict the segregation in ingots and how to use them in industrial conditions. At the beginning I will tell you a few words about the Industrial Soft, the company that has developed the software used in this analysis, and then I will make actually the presentation. Industrial Soft is a Montreal, Canada-based company specialized in ingot mold design and development of simulation software with application in improving the internal quality of forging ingots. The company is managed by Evgeny Bogdan, a material engineer who worked for more than 10 years in a forging and steel-making shop. He has experience in improving the internal quality of ingots and made several mold projects for pouring ingots between 50 and 250 tons. In this presentation first, I will provide a short description of macro segregation type that has been taken in account, then the tools and the technique I use to analyze the influence of various manufacturing variables on segregation. After that, I will present how the ingot size and geometry, casting technology variables and chemical composition have influence on segregation area size. At the end of presentation, I will show you a few examples to demonstrate practically how we can use the results to choose the ingot size and geometry to minimize the macro segregation area size, and finally, the results of the solidification simulation for an ingot having in view the thermal isolation of the hot top. The analysis and the technique I will present refers to segregation, one of the types of macro segregation. We can find this kind of material heterogeneity in the zone of transition from columnar grains to large equiaxed grains. This segregation presents channels enriched by carbon, phosphorus and sulfur, and can be put in evidence by sulfur print test, and has as result both defects detected by ultrasonic test and heterogeneity of material and mechanical properties. In this slide we can see the segregation position on the longitudinal section of the ingot. Next, it's a sulfur print test taken in the segregation area, and at the bottom, the map of ultrasonic test for a forged bar. Here, I'd like to make a small note. Sometimes the ultrasonic test does not detect the segregation channels. Instead, as observed in real products, because of the material heterogeneity we can have problems to meet the specifications concerning mechanical properties. So, if we like to avoid this kind of problems, we have to control the segregation process, and one of the ways it's to choose the right ingot size function by the chemical composition of the steel. In this slide I present SimCAD v.2.0. the solidification software we have developed to simulate the solidification and control the segregation process. The software takes into account the initial temperatures and thermophysical properties of the steel poured, mold material and refractory bricks. Here, I have several applications to demonstrate the possibilities of the simulation software we have developed. First example shows the solidification profile of an ingot and segregation prediction. The second one shows the solidification profile and the simulation of axial porosity into a steel ingot. Third example shows the simulation of porosity in steel castings, and the last one, an application in the heat treatment area. The software has been validated in industrial conditions several years ago in cooperation with Cosepa, a steel-making company in Brazil, and the results have been published into a technical magazine. See the list of references we have at simcad.com to get the paper and learn more about the conditions of the validation of the heat transfer software. This flowchart presents the macro segregation prediction technique we have developed and implemented in the segregation prediction module of the software. This technique is based on Suzuki and Miyamoto method, the most used way to predict segregation in steel ingots. As you can see in this flowchart, there are two branches. The left one calculates by simulation the cooling and solidification rate. This branch has as input data the ingot geometry, material properties and initial pouring and mold temperature. The other branch calculates, using the chemical composition of the steel, the critical value alpha, the value at which the asegregation will appear. Then, the software compares the values we got from both branches and plots the segregation area in regions that contain values below the critical value. So, we have two situations. In the first case, if the solidification rate is bigger than the critical value alpha, as seen in the bottom left side example, we do not have segregation. In the second one, if the solidification rate is lower than the critical value alpha, we will have asegregation, and its intensity depends on the difference between solidification rate and critical value alpha. At the moment, the asegregation prediction technique can be used only for carbon steel and low alloyed steels. To extend the applicability to stainless steels, T-alloys or other exotic materials, we need to establish the critical value alpha using an experimental apparatus as presented in this slide. Here is an example of typical mold assembly and ingot take as input data for the solidification simulation software. In the first table is the geometry data of the analyzed ingot. Here, the H/D ratio is defined as ratio between body height and medium diameter. The ingot taper is defined as the ratio between difference of diameters at top and bottom and the height of the body. In the next table is the chemical composition of the steel I took to calculate the critical value alpha, and in the last table are the thermophysical data of the analyzed system. Using the principle mentioned before, we made several numerical experiments to analyze influence of manufacturing parameters on macro segregation in a 50T ingot steel. In these experiments we analyzed influence of casting technology variables, mold geometry, and chemical composition of steel on macro segregation. From the first category of variables we analyzed the hot top size, from the second one H/D ratio, and from last one the influence of C content on macro segregation area size. More information about these experiments I will give to you in the next slides. In the next slides you will see how the H/D ratio, ingot taper and mold thickness have influence on the macro segregation area size. To analyze the influence of ingot H/D ratio on asegregation, I made two simulations. For one of them, the ingot H/D ratio has been 1.5. For the second one, the H/D ratio has been 2.0. The weight of both ingots has been 50 tons. These pictures presents the solidification profile of the ingots and asegregation prediction I got by simulation. The parameter Rs is defined as the ratio between area affected by segregation and the total area of the longitudinal section of the ingot. As seen in these pictures, in both ingots the segregation will appear. The area affected by segregation is larger if the H/D ratio is low. So, if we like to minimize the macro segregation in this particular ingot, a high H/D ratio is recommended. To analyze the influence of ingot taper on asegregation, as in the previous case, I made two simulations. For one of them, the ingot taper has been 9%. For the second one, the ingot taper has been 11%. In both cases the ingot weight has been 50 tons, as well. As we can see, the area affected by segregation is larger if the ingot taper is high. One of the reasons is the increasing of diameter at the top of ingot and a lower solidification rate. So, to minimize the macro segregation in this ingot is recommended a low ingot taper. To analyze the influence of mold wall on macro segregation I made two simulations as well. In one of them the wall thickness has been increased with 100 mm, from 350 to 450. As we can see, the area affected by asegregation is not much influenced by wall thickness. The segregation area size is only 1% lower by increasing the wall thickness with 100 mm. In the next three slides I analyzed the influence of hot top size, initial mold temperature and pouring temperature on asegregation. To analyze the influence of hot top size, I made simulations with hot top ratio of 20, 30 and 40%. As you can see, the area affected by asegregation is lower if the hot top size is small. So, to minimize the asegregation in a 50 tons ingot, a small hot top is recommended. This slide presents the influence of initial mold temperature on asegregation. The simulation has been made for initial mold temperature of 20, 200 and 400 Celsius degrees. The area affected by asegregation is lower if the mold temperature is low. To analyze the influence of pouring temperature on asegregation, I made simulations for 1540, 1570 and 1600 Celsius degrees. As we can see, the asegregation area size is lower if the pouring temperature is low. So, to minimize the asegregation, a low pouring temperature is recommended. In the next 4 slides I will present to you the influence of carbon, sulfur, silicon and molybdenum content on segregation in the 50 tons ingot. To analyze the influence of carbon on segregation, the critical value alpha has been calculated for 0.35, 0.40 and 0.45% of carbon. The results of simulations show that the segregation area size increases with the increase of carbon content. To minimize a segregation area size, a carbon value at minimum limit provided by specification is recommended. To analyze the influence of S content on asegregation, the critical value has been calculated for S values of 0.002, 0.01 and 0.02% of sulfur. As expected, the asegregation area size increases with the sulfur content. In this slide is presented the influence of silicon content on asegregation. The silicon value I took for calculation of critical value has been 0.10, the minimum limit allowed by 4340 steel specification, 0.23, the medium value, and 0.35, the maximum limit allowed by specification. As we can see, only by using the silicon content at the minimum limit allowed we can reduce strongly the asegregation in the 50 tons analyzed ingot. Having in view a technology like VCD, we can lower the silicon content at values even lower than 0.10, and so making possible to get ultra-clean steels as the 700 tons ingot poured by Japan Steel Works. Also, using silicon at values less than 0.10% can be a suggestion to develop not only new materials but also a motivation of using clean technologies as VCD. To analyze the influence of molybdenum on segregation, the critical value has been calculated for 0.10, 0.28 and 0.35% of molybdenum. As we can see, by varying the molybdenum content, we can control the segregation area size, as well. If we can utilize a smaller ingot, we can avoid segregation at lower value of molybdenum. This can be a way to minimize the manufacturing costs by minimizing the ferromolybdenum consumption. The following example is about how to use the macro segregation prediction technique to choose ingot geometry to minimize macro segregation. In this example, we assume that there are available 3 types of molds with H/D ratio 1.0, 1.5 and 2.0. Macro segregation we get by simulation is given in the first set of diagrams. From the analyzed ingot types, we choose the ingot with H/D ratio 2.0, ingot with the lower segregation area. In this example, the segregation area can be reduced more by increasing molybdenum and reducing silicon content. Please note that in this slide is shown the distribution of cooling rate at half of the ingot height. The following example is another application in casting technology design stage. A 5 tons ingot with the geometry given in this slide has been taken into consideration. After simulation and segregation prediction, we find out that there is not segregation even if the molybdenum content is at minimum value allowed by steel specification. This suggests that we can lower manufacturing cost of the ingot by lowering molybdenum content of the steel. The values in this table shows how much we can save if we use a lower molybdenum content. The following example demonstrates how to use the macro segregation prediction in steel making shop. Steel making process is sometimes unpredictable and may be situations when we cannot control the content of carbon, silicon, sulfur or phosphorus. Using macro segregation prediction, we find out that in the programmed ingot will be segregation at an unacceptable level. In this situation, we have two options to avoid the segregation: either increase the molybdenum content or simply change destination of steel by using a smaller ingot. Using segregation prediction, it can be generated a quality certificate with information about position, area size and intensity of macro segregation for a particular ingot size and steel, information useful in design of forging technology. This slide presents an example of a such certificate we can generate. This example is about how to use the macro segregation prediction if you like to acquire an ingot. Macro segregation prediction can tell you if an ingot with a particular geometry and chemical composition is free of segregation or not. The first ingot in this slide has a very large macro segregation zone and is not recommended to use it for making high-quality forgings. In the second one, the macro segregation area size is almost zero and it can be used to manufacture forgings with high quality. In the next 3 slides I will present to you the influence of hot top isolation on asegregation for a 4 tons 4140H ingot. In this slide is displayed the solidification profile of 4 ingots having various thermal isolation. The hot top of the first ingot has not been isolated, the second one has been isolated with a thermo-isolant material. For the third ingot has been used exothermic material, and for the last one the hot top is isolated perfectly. Analyzing the data we got by simulation, we can observe that the solidification profile inside the body of all 4 ingots is practically the same in the area where the segregation occurs. The only change is the solidification profile of the hot top. It does not matter the type of isolation that has been used. Indeed, if we exclude the first ingot where there is not isolation, the segregation area is practically constant for all other ingots. So, we can conclude that the isolation type of the hot top does not have influence on the segregation area size. In this slide is presented the axial porosity prediction using the NAMA criterion, the most used criterion to predict porosity in steel ingots and castings. The next 3 slides present the solidification profile and segregation prediction for nickel-chrome molybdenum ingots. The ingot size has been between 14 and 30 tons and H/D ratio between 1.4 and 5.0. The solidification time for these ingots is between 4 and 11 hours. In this slide is the asegregation prediction. The last 3 ingots have practically the same weight, and as we can observe, the segregation area size is lower if the H/D ratio of the ingot is high. As reported in some technical papers, to avoid axial porosity and pipes we have to choose an ingot with low H/D, but if we like to have a homogeneous material without segregation we have to choose an ingot with high H/D ratio. As a result of this presentation, we can say that it is possible to control the size and intensity of segregation by changing ingot geometry and its chemical composition. So, the solidification simulation software and macro segregation prediction technique I presented to you are useful tools that can help to choose ingot size, geometry and the chemical composition of the steel in order to minimize segregation and increase the homogeneity of forging products. Based on solidification simulation software and segregation prediction technique I presented to you, we can optimize ingot size and geometry, chemical composition, steel making and pouring technology in order to minimize the risk of finding defects at ultrasonic test. Choose a target chemical composition for a particular ingot size and steel grade to minimize segregation and increase the homogeneity of mechanical properties. Choose ingot size and geometry function by steel grade. Analyze the manufacturing variables analysis and macro segregation prediction for a particular steel grade and ingot geometry. I finished my presentation and I would like to thank you for listening to, and if you like to ask questions, please contact us at the address you see on the screen.